Okay, so we have two wave sources here. The waves propagate from here, they overlap, and we get constructive and destructive interference. Let's first draw out one antinodal line. Antinodal line is where we get constructive interference. So obviously, right at the middle, you get one antinodal line. Every point along this line is equidistant from S1 and S2. So the waves will travel the same distance before they superpose. Therefore, they will superpose in phase, resulting in constructive interference. So this one is quite obvious. Of course, there are other antinodal lines. Just look for points where the two crests intersect, like here and here and here. I think it's quite natural for us to join all these points together. When you reach here, you just continue and position this to be midpoint between these two crests here. So we are going to get constructive interference along this line as well. Let me just quickly explain to you why this is so. For example, take this point here. At this point, we are 1, 2, 3, 4 wavelengths away from S1. From these points, we are also 1, 2, 3 wavelengths away from S2. So 3 and 2. So the path difference is 1 wavelength, right? And not just at this point, at any point along this line. Maybe I'll pick this point. This point is 1, 2, 3 3.5 wavelengths from S1. But it is 1, 2, 2.5 wavelengths from S2. So 3.5, 2.5. So the path difference is again 1 wavelength. In fact, any point along this line, the path difference is always one wavelength. It's always 1 wavelength further away from S1 compared to S2. That's why this could be called the n is equals to 1 antinodal line, whereas this is the n is equals to 0 antinodal line. So clearly there's going to be a n is equals to 2 as well. Again, look for the points where the crests intersect. So you find it here, all these crests intersecting. You can trace it all the way here. And this is the n is equals to 2 because any point along this line, we are always 2 wavelengths further away from S1 compared to S2. Of course, there's n is equals to 3. Again, look for the intersecting points and you find it here. Just trace it, and when you reach here again, plonk it to be right at the middle between two crests, and we get the n is equals to 3 antinodal line here. If you want, you can do a quick check. For example, take this point here. This point is 1, 2, 3, 4, 5 wavelengths away from S1, and it's only 2 wavelengths away from S2. So 5 and 2, that's why the path difference is 3 wavelengths. You can check these points as well. This point here, 1, 2, 3, 4, 4.5 compared to 1.5. So the path difference is 3. Of course, we have a mirror image of things on the other side. Let me just quickly trace them out. Again, just look for the points where the two crests intersect. Okay, so A, B, and C, D are actually antinodal lines where the path difference is 4 wavelengths. So it should be clear to you now that there are these 7 antinodal lines between AB and CD. Okay? And where would we find the destructive interference? So let me sketch the nodal lines, which should be right in the middle of 2 antinodal lines. Just draw them to be in the middle of 2 antinodal lines. The logic is quite easy. Any point along this line has a path difference of 0. Any point along this line has a path difference of 1. To get destructive interference, we need a path difference of half, 1.5, 2.5, and so on. So those lines have to be found between two antinodal lines. Okay? So just draw any of these red lines I've drawn, or uh, any of them on the left side will do as well. Okay, that's all I have to say. Ta-ta!